Hello everyone. So in continuation from our last class, this is MSD 02 Manual Structural Design, and we're starting with classification of structures according to dimensions. So we'll be looking at one-dimensional structure, one-dimensional structure. A structure is said to be one-dimensional if the dimension of one of the side is so large compared to others. Compared to other sides, one-dimensional structures are example, e.g., columns. Column is a one-dimensional structure because one of the side is so large compared to the other sides. So you have our columns, our beams, they're all one dimensional. Retaining walls, etc. etc. Then two, we have two-dimensional structures. For two-dimensional structures, two-dimensional structures are structures that two of the sides are so large compared to the other side, like the slab. Example, we see the slab. Let's take this as a slab. You see that both sides, these two dimensions, the x and the y axis, are large compared to the thickness of the slab, which is minimum of 150 mm, right? So this could be a slab. So this dimension and this dimension are so large compared to the thickness, which is usually just 150 mm. This could be 4000 mm by 3000 mm. So your slab, examples of two-dimensional structures, you have your slab, walls, deep beams, deep beams, etc. Right? These are your two-dimensional structures. Then for three-dimensional structures, number three, the structure is said to be three-dimensional if three of the dimensions are closely equal in magnitudes. If three of the dimensions are closely equal in magnitude, it becomes a three-dimensional structure. Example could be the foundation of a structure. So foundation. Okay, so that will be that for classification of structures according to dimension. Now let's look at classification according to static equilibrium. So we have classification So classification of structures according to static equilibrium. So to classify structures according to static equilibrium, we have the determinate structures. Statically determinate structures. A structure is said to be statically determinate if it can be analyzed by using the three equations of equilibrium. So a structure is said to be statically determinate if it can be analyzed using the three equations of equilibrium, which are the sum of the forces in the horizontal axis equal to 0, sum of vertical forces equal to 0, and then the sum of moment at the point is equal to 0. So this is 1, 2, 3. These are the three equations of equilibrium. So if a structure can be analyzed using these three equations, then it is statically determinate structure. Then two, we have the statically indeterminate. A structure is said to be statically indeterminate if it cannot be analyzed using these three equations. So for such structures, a more compatible equations will be generated, right? Will be generated. Okay. So now let's look at support conditions. Support conditions. Support conditions in structures. We have the one roller supports. Roller supports. A roller support is free to move in the direction of the roller when subjected to applied force, and therefore will only resist or generate a reaction that is perpendicular to the direction of the roller. Example is practically your sliding glass, your windows. Sliding glass for windows in building. So that's the roller support. Then two, we have the pin or hinge support. So for your pinned or hinge supports, these are support that can resist translational displacement due to vertical and horizontal forces but not rotational. Therefore, it will only generate two reactions. So they only generate two reaction. Example is your door hinge, your door opening your door hinge to the frame, and then a beam and the column connection in the building. They can be monolithic, huh? So the forces will only be your two reaction without moment. So for a pin and hinge support, you have your door, a door hinge, a door hinge to the frame, and then a beam and column that is connected in buildings that are monolithic. So number three, we have the fixed or rigid support. For your fixed or rigid support, this support type is not free to displace in any direction but fully restrained against displacement. In essence, it can resist both translational and rotational displacement, and therefore will generate three reactions. Example of this kind of fixed or rigid support is the foundation of a building connected monolithically to the earth. So the starter reinforcements, for example, of a column and the foundations are fixed together. So I'll just say example of this, your foundation of a building. So connected monolithically to the earth, that is your starter bars connecting to your column, so to the pad base. So it's fixed completely. So okay, to give a diagram, show how the roller supports is, this is how you represent your roller supports. This roller support supporting this, then this is your hinged for your hinge, this one, two for your pin on hinge support. It is represented this way, carrying a load. So this is represented. Then number three, for your rigid or fixed, you have this practically the diagram. So for this, reaction is only on one side. So for this, number one, reaction is on one axis, R1. Your reaction is only on one axis. Then for your pinned or hinge supports, you have two reactions. So this will give two reaction. You have the vertical reaction, which would be like the sum of forces, and the vertical is equal to 0. Then you have the horizontal reaction. So you have R1 and R2 for your pinned supports. Then for your rigid or fixed supports, you'll be having three reactions. You have the upward reaction R1, you have the horizontal reaction R2, then you have moment R3. So this is practically how these support conditions could be represented. So I'd like to end the class here for today. Continue in our next class with analysis of the determinate beam. Start. So this is how these supports could be represented, and this is the free body diagram for ruler supports. Is a free body diagram for a pin or hinge support, and this is the free body diagram of a fixed or rigid support. So see you in our next class.